Alright, so we're going to pick back up with horizontal asymptotes. This is the third characteristic about rational functions that we're going to find. And so, one thing that you need to be aware of with horizontal asymptotes that's different from vertical asymptotes is vertical asymptotes, the graph is never going to cross, because those are places where the graph is undefined. Those are the places where zero, the numbers that would make the bottom zero. So, a horizontal asymptote is a graph can cross it. So, in some places it's going to cross that. Because this is not an undefined place. Horizontal asymptotes are just used to determine the end behavior, and what that is what happens to the y values as we get way far out. So like the negative infinity or positive infinity on the x-axis, what's the y values doing? So there are some rules that you have to follow when finding horizontal asymptotes, and I'll hopefully tell you a way that'll make it easier to remember these in just a second. But if the top degree is smaller than the bottom degree, and what I mean by degree is if you have a function, let's just add a page. If you had a function like this, x squared plus 3x plus 2, the degree would be 2. If you had x cubed plus x squared plus 1, the degree here would be 3. Okay, and so all the degree refers to is just the exponent that is largest. Okay, so it's the largest exponent. So even though this has a 2 in it also, the degree of this function is 3 because this is the largest exponent. So if the top degree is smaller than the bottom degree, or if the bottom is bigger than the top, then y equals 0 is the horizontal asymptote. Okay, so if the bottom is bigger than the top, horizontal asymptote is y equals 0 every time. Now, if the top degree and the bottom degree are the same, then you're going to take, it's going to be y equals the leading coefficient of the top and divide it by the leading coefficient of the bottom. And what I mean by leading coefficient is if this had a 2 and this had a 4, then the leading coefficient here would be 2, because it's the number in front of the term that has the degree, or the largest degree. This leading coefficient would be 4 because it's in front of the term that has largest degree. If I even had something like this, x plus 2x squared plus 3, and my terms were out of order, just because this term is leading doesn't mean it's the leading coefficient. The leading coefficient would not be 1. Leading coefficient would still be 2 because it's the number in front of what has the degree. So, leading coefficient divided by, of the top divided by leading coefficient of the bottom. And then if the top degree is bigger than the bottom degree, then you have no horizontal asymptote in your graph. So, these are some rules that you have to go by to find them. The way that I remember these is with the acronym Boston. So, this is the way that a lot of people remember them. If the bottom is bigger, okay, so bottom is bigger, then y equals 0 is your asymptote. If they're the same, and then this one's you just have to kind of go with it because it's not really that creative, but it's just the top divided by the bottom. Okay, so the top number, I just put top number divided by bottom number, and we know that number is the leading coefficient. And so then if the top is bigger, then you have no, it spells no if you go up this way, no horizontal asymptote. And so that's just how I remember that. If it helps, great. If it doesn't, just forget about it. But anyways, I think it sounds like it makes sense. If you do bottom is bigger, y equals 0, it just sounds right. Anyway, let's use these rules to find all of our horizontal asymptotes. So let's find the horizontal asymptote of this function. So the bottom is bigger. So if the bottom is bigger, then y equals 0 is my horizontal asymptote. So y equals 0 is horizontal asymptote. And I'm going to show you on the calculator what a horizontal asymptote looks like. So let's plug this in. I'm going to plug in 2x divided by 3x squared plus 1. So 3x squared plus 1. And so I'm going to go ahead and I actually do need to put parentheses around this top part as well. So I'm going to parentheses around the top and the bottom. And so then if I look at my graph, Here it is. And so now you can see that the horizontal asymptote is y equals 0. That's my horizontal asymptote. And so you can see that this graph crosses that horizontal asymptote right here in the center. But as you go way far out on the x-axis towards negative infinity, the y values, or the graph, gets really close to 0. Okay, same thing towards positive infinity. Y values get close to whatever that number is for the horizontal asymptote, and this one is just 0. So you can also see that by looking at the table. So if you scroll way far back, you can see that those y values are getting closer and closer to 0 the further you go. Same thing would happen if we scrolled to the positive end. So horizontal asymptote is just y equals 0. The second one, same function. The only thing that's different is here the degree is 2 instead of 1 in the top. So since they are the same, then I'm just going to take the top coefficient divided by the bottom coefficient. And so the top coefficient is just 2. The bottom leading coefficient, even though it's not in front, is 3. And so 2/3 is my horizontal asymptote. So I'm going to change this function in my calculator, and we're going to look at it. So 2x squared. Let's change that, 2x squared. Alright, over 3x squared plus 1, so I'm going to graph. And so you can see that this one doesn't cross that 2/3, but it does, as we go way out on the x-axis to the negative infinity and positive infinity, get really close to 2/3. And you can check that decimal by looking in your table. And so you can see it's getting close to 0.66666666, which is just 2/3 way out here towards the negative end. If you were to go to the positive end, it'd be the exact same way. Alright, so third, we're going to have the top degree bigger than the bottom degree, and so when that happens, you have no horizontal asymptote. So we have no horizontal asymptote. If we were to plug this in and look at it, we're going to make this a raised to the insert of 3. And so you're going to see it doesn't have a horizontal, but it has a different kind of asymptote. And this is a slant asymptote. And so it's just when the graph is slanted towards a certain number. And we'll learn how to find those here in just a second. Just a second. Alright, so this one has no horizontal asymptote. So those are our rules for horizontal asymptotes. Not too bad. Now, a slant asymptote. These occur when the top degree is exactly one more than the bottom degree. And so the reason that we did our long and synthetic division is because that's how we're going to find slant asymptotes. So the amount that the bottom goes into the top evenly is the slant asymptote. So what I'm going to do is take the bottom, divide it into the top, and whatever comes out evenly up here is what my slant asymptote is going to be. So we don't care about the remainder. You don't give a care about the remainder when you are finding slant asymptotes. So I'm going to go ahead and put a plus 0 on the end here. So what would I have to multiply by x to get x squared? That's just x. So x times x is x squared. X times 1 is just a positive x. But I'm going to change those signs. So this is going to be minus minus. Those cancel, and I'm left with a negative 2x. So I'm going to bring down the 0. So then x would go into negative 2x a negative 2 time. And so then I would say negative 2 times x is a negative 2x. Negative 2 times 1 is negative 2 when I change the signs. The remainder is 2, but I don't care about this. The amount that it goes evenly is y equals x minus 2, and this represents the equation for my slant asymptote. And so I'll show you what that looks like on the graph. But you always need to put y equals in front of this, because this is an actual line that the slant asymptote is. So it's an actual line. Again, it's not part of the graph, it's just what the graph follows. We'll represent it on our graphs with a dotted line. So let's plug this in. Our function is x squared minus x over x plus 1. So x squared minus x divided by x plus 1, and I'm going to delete the rest of this. So when I graph it, we can see that it's kind of going out on a slant line. And so the way, if you wanted to check your slant asymptote, is I could plug this in. Again, this is not part of a line on the graph. This is just to check to see that your slant asymptote is correct. But I could plug in x minus 2 here and see that the graph is never going to touch this line. So see how it goes straight through those? It never touches it, gets really close. That's what our slant asymptote is. It's not actually part of the graph, so I'm going to clear that out. Alright, but this is our slant asymptote. We'll do two more. Alright, so this one, we're going to take x minus 1. We could actually, instead of doing long division, you could do synthetic division on this because this is a linear factor in the bottom. So I'm going to go ahead and do that since it'll be a little bit easier. And so then I'm going to put 1 out there. My coefficients will be 1, -1, and -2. So I'm going to bring down my 1. 1 times 1 is 1. That'll be 0. 1 times 0 is just 0. So my remainder is -2. I really don't care about that. Doesn't give me anything when it comes to slant asymptotes. And so this is just going to represent y equals x for my slant asymptote. We go down a degree from here to here. So y equals x would be my slant asymptote. You could check that on the calculator. Last one. Now, you have to divide the original bottom piece into the original top piece. So if we were to factor this, like if I asked you to find all the discontinuities, you would find holes, vertical, horizontal, everything. Okay? We can't take the factors, or the factored form, and then after we cancel it, we can't take that and then do our long division. You have to take the original problem and do your long division to find the slant asymptote. So I'm going to take x squared minus 4 and divide it into 2x to the third plus 5x squared minus 13x minus 30. And I'm going to have to do long division on this one because this is not a linear factor in the bottom. So I'm going to have to do the long division. So x squared, I would have to multiply that by 2x to get the x cubed. So then 2x times x squared is 2x cubed. 2x times -4 is just a -8x. So when I change my signs, that's going to give me a 5x squared, and then this is going to give me a minus 5x minus 30. So then I'm going to say, okay, x squared, what would I have to multiply it to get 5x squared? And that's just a positive 5. So I would say 5 times x squared is 5x squared minus 20. If I change the signs, that's going to give me a -5x minus 10. And then this is going to end up being my remainder right here because there's nothing that I can multiply by x squared to get -5x. So I'm done. Don't care about that remainder. And so my y equals 2x plus 5 is going to be the slant asymptote for this function. And so again, you could check that on the calculator if you wanted to.